All right, let's talk about something huge. What if I told you there was a secret rule book for, well, for the entire universe? A single set of laws that dictates how everything moves. And I mean everything. Well, that rule book has a name: mechanics. Think about it for a second. A planet, gracefully orbiting its star, and a simple ball flying through the air. I mean, they couldn't seem more different, right? One's this grand cosmic dance and the other's just a toss. But what if they're actually following the exact same rules? Yup, that's the big secret. The answer to both is a single set of rules called mechanics. It's this beautiful, elegant framework that explains it all, from the biggest galaxy down to the tiniest speck of dust. So today, let's dive in and see how it works. Okay, so first things first. Before we can even get into the why of motion, we gotta have a way to talk about the how. We need a language to describe where things are and where they're headed. This is the absolute foundation for everything else we're gonna cover. And that language? It's called kinematics. Seriously, just think of it as the what and where of motion, not the why. We're not getting into forces or energy or any of that stuff yet. For now, we're just being detectives, just observing, measuring, and describing what we see. So the vocabulary of kinematics really boils down to three simple questions. First, where is it? That's its position. Second, how fast is it going and in what direction? That's its velocity. And yeah, the direction part is super important. And third, is that velocity changing? Is it speeding up, slowing down, or changing direction? That's acceleration. That's it. Those three ideas are the building blocks for describing literally any movement you can imagine. And with that vocabulary, we get these awesome tools. These equations are like the grammar of motion. If you know an object's acceleration is steady, like a ball falling due to gravity, you can plug in the numbers and predict exactly where it's going to be and how fast it'll be going at any point in the future. It's like having a crystal ball for moving objects. All right, so we've got the language down. We can describe motion perfectly. But now we get to the really big question. What actually causes things to move? What's the engine behind it all? Well, it's time to open up the official rule book, written by none other than Sir Isaac Newton himself. Newton's first law is often called the law of inertia, but I like to think of it as the law of cosmic laziness. It basically says that objects just want to keep doing what they're already doing. If it's sitting still, it wants to stay still. If it's moving, it wants to keep moving in a straight line at a constant speed. It won't change unless something comes along and forces it to. So what is that something that forces a change? Well, it's a force. And this brings us to Newton's second law, and probably the most famous equation in all of physics, F equals ma. This is the heart of it all. It tells you exactly how much an object will accelerate when you push or pull on it. More force, more acceleration. More mass? Well, it's harder to move, so you get less acceleration. Simple as that. And then there's the third law, which is all about teamwork. It says that forces never, ever show up alone. They always come in pairs. You push on a wall, guess what? The wall pushes back on you with the exact same force. It's how rockets work. The rocket pushes hot gas down, and the gas pushes the rocket up. For every action, an equal and opposite reaction. Every single time. And that's basically it. Those three simple laws, that's the core of dynamics. That's the rule book for how forces create motion. From a baseball to a planet. It's incredibly powerful when you think about it. Okay, but wait. There's another way to look at this whole puzzle. It's just as powerful, but it comes at it from a totally different angle. Instead of thinking about pushes and pulls, let's start thinking about the currency of the universe. Let's talk about energy. Yeah, you can really think of energy as the universe's cash. If you want anything to happen, if you want to make something move or heat up or change in any way, you have to spend some energy. The craziest part, though, is that you can't create or destroy it. The total amount of energy is always the same. It just gets passed around and changes from one form to another. That's the famous law of conservation of energy. Now, in the world of mechanics, we're mostly interested in two main types of this energy cache. First, you've got kinetic energy. That's the energy of doing stuff, the energy an object has just because it's moving. Then you've got potential energy. That's stored energy. It's energy that's just waiting to be unleashed, like when you hold a ball up high. It's got potential energy just from its height, ready to go. A swinging pendulum is the perfect example of this. At the very top of its arc, it pauses for just a split second. Right there, all its energy is potential. Then, as it swings down, that potential energy transforms into kinetic energy, and it's moving fastest at the very bottom. Then it swings back up, turning kinetic back into potential. The whole time, the total amount of energy stays exactly the same. It's just trading back and forth. So, we've got straight line motion down. But the universe isn't all straight lines, is it? I mean, things spin. Planets spin, galaxies spin, a figure skater spins. So does that mean we need to throw out our rulebook and start all over again? No, not at all. And this is the beautiful part. We don't need new rules. We just need a new vocabulary, a new dialect for the language of motion. For every single concept we just learned, there's a rotational version. A push or pull, a force, becomes a twist, which we call torque. An object's resistance to being moved, its mass, becomes its resistance to being spun, its moment of inertia. It's all just a direct translation. Let's zoom in on that one for a second. Moment of inertia. It's just a fancy term for rotational laziness. It's how much an object resists being spun. And it's not just about how heavy something is, but where that weight is. Think about a figure skater. When they pull their arms in, they spin faster, right? That's because they're decreasing their moment of inertia. When they spread their arms out, they slow down. Same person, same mass, just distributed differently. So you see, Newton's laws still work perfectly. You apply a torque, you get a change in spin. It's exactly the same fundamental physics we've been talking about, just, looking at the world of rotation instead of straight lines. Okay, let's put all these pieces together now. We've got the language, we've got the rules for forces, and we've got energy. Let's zoom way out and see how these simple ideas create the incredible rhythms and patterns of the entire universe. For centuries, people like Kepler figured out how the planets moved in their neat little orbits, but nobody knew why. Then Newton comes along with his law of universal gravitation, and boom, he realized that the very same force that makes an apple fall from a tree is the exact same force that keeps the moon circling the Earth. He connected the heavens and the Earth with one single, beautiful equation. And this cosmic dance, this constant pull of gravity, sets up rhythms all over the place. I mean, you have the slow, epic rhythm of a planet going around the sun, but you also see rhythm in things like a pendulum swinging, a guitar string vibrating. Nature is just packed with these repeating motions, or oscillations. And there's a special name for the most fundamental kind of rhythm, simple harmonic motion. All that means is that whenever you have a system where the further you pull something away from its happy place, the harder it tries to pull itself back. A kid on a swing, a mass on a spring, that's the basic recipe. And this simple idea is the secret behind pretty much everything that wiggles, vibrates, and oscillates in our universe. So there you have it. From figuring out the path of a thrown ball to understanding the dance of entire galaxies, mechanics is the rulebook. It's just incredible that a handful of elegant, simple laws can explain so much of our moving universe. It really makes you wonder, right? What other rulebooks are still out there, just waiting for us to discover them?